Okay, so let's begin our second talk. And we're very happy to have Li from Yao Center at Tsinghua University to speak on vertex algebra, quantum master equation, and mirror symmetry.
Yes, thanks very much for the invitation. It's a great honor for me to speak at this JDG conference. I'll be talking about this vertex algebra, quantum master equation, mirror symmetry. So here's the outline. I will start with some motivations as an introduction, and then I will describe a so-called B-quantization method. I'll explain what this one means, and then I'm going to apply this quantization method to study some kind of two-dimensional problem, which is a higher deformation of conformal field theory. And as application, I will describe something related to mirror symmetry and integrable hierarchy. So let me start with the motivation. What's happening? The motivation comes from actually trying to understand the relationship between this triangle, like topological string and Hodge type theory and integrable hierarchy. And we know this kind of integrable hierarchy just appeared universally in this story for a Gormitian type theory. So we will understand what's happening here from some kind of a Hodge type theory. So here's actually the motivation for this, work. And it's about this formula. Exponential function has a Taylor series expansion. Actually, everybody learns this formula from freshman calculus. And actually, this talk will be mainly trying to understand this formula. So in which sense? First of all, you observe that if you promote this function u to be a function of the variable u to be a function of one variable, and it introduce the Poisson bracket by this formula. So the bracket of u, x, and uy is a derivation of a delta function. Then you observe that you find infinite many pairwise commuting Hamiltonians. So this function commutes with respect to this Poisson bracket. And actually, this is a dispersion list, a KdV integrable hierarchy. And this is related to the problem that come from trying to ask why integrable hierarchies appear naturally in topological string, and whether this kind of exponential formula is universal. It turns out to be yes. And this, the Gromitian type way to understand this formula is by saying that this function is basically the so-called primitive form for A1 type singularity, and the right-hand side is basically the period map, which corresponds to some kind of higher deformation of free boson. I will try to explain what's happening. That's one motivation. The second motivation comes from mirror symmetry stuff, and Professor Jun Li just gave a very a discussion on this history, so I'll be very brief. So this kind of mirror symmetry links this A model to B model, symplectic complex. And here you have this Gromitian type theory, and the B side has Hodge type theory. For example, if you count rational curves, you got this variation of Hodge structures. And the natural question is if you count higher genus curve, and what's happening on the B side, which amounts to some quantization of this variation of Hodge structure on Calabi-Yau geometry. And it turns out these two problems are closely related. This quantization, this B model geometry, and the integrable hierarchy. So this talk I will be focused on B model as a mirror of Professor Jun Li's talk. So actually, this is also mentioned in the previous talk that around 1994, physicists like Bajeshki, Sakodi, Grivaffa, they proposed that a B model on Calabi-Yau threefold can be described by so-called Kodawa-Spencer gauge theory. And this actually turns out to be describing the Zilbach stream field theory in the topological B model as a leading approximation. And later on, what's happening? Okay. I will use this. So later on, with Castello, we actually find a full description in the B model by turning on so-called gravitational descendants. And this is works for any Calabi-Yau. We're going to call this one B series theory. And actually, a general method to quantize a gauge theory is a so-called a B-way quantization. I'll explain this notion later on. But let's assume we can do this one for this particular interesting gauge theory. And I'm going to denote this notion by the B-way quantization on X for this particular BCU theory, just a symbol. Then we have this kind of like a quantum higher genus mirror symmetry conjecture from BCOE and also generalized in our version, which says that if you look at the mirror Calabi-Yau geometry, and you let this one to be the Gromitian type theory of counting curve in the A model, then this Gromitian theory somehow is mirror to this B-way quantization on the mirror Calabi-Yau for this particular type of BCO theory. And if you go to the classical limit or this counting genus zero curve, and this one turns out to be related to Saito's primitive form in the non-logarithm model, also called a Barnikov-Kansevi semi-infinite period map for the Calabi-Yau models. And this mirror stuff just reduces the classical mirror symmetry for counting rational curves. And for example, you can show this mirror conjecture holds on elliptic curve. I'll give a brief account of this theorem later on. Just a remark. When this genus zero theory is so-called semi-simple, and there exists some other approach to this higher genus B model. For example, there's a give and tell and de Boer-Zhang's higher genus formula. And you can use this formula to do non-logarithm B model without OP folding. If you work with compact Calabi-Yau, which is never semi-simple, and you can also approach B model from so-called a categorical way. And this is mainly developed by Castello. And actually, recently, Kadaruran too, they verified a subsector of this higher genus mirror symmetry on elliptic curves for one-point function using this categorical B model. So this is some related works. Now, let me come back to the motivation at the beginning to understand what's happening for this integrable hierarchy. It turns out to be something very strange, but let me try to explain. Suppose X in the Calabi-Yau geometry. Now, you look at another Calabi-Yau, a one-dimensional Calabi-Yau. So this is like a C or C star elliptic curve. And you look at this product space and look at a trivial fibration. Geometrically, this is very naive. Then because this is a product space as a Calabi-Yau, you look at the B model on this product space in terms of this BCO theory, for example. You can do some other stuff. And you can construct a push-forward functor as actually in the category of so-called B-way quantization, roughly speaking. You get some kind of a quantum field theory, 2 dimensions, living on this one-dimensional Calabi-Yau. And it turns out that this particular theory is a chiral deformation of conformal field theory in 2 dimensions. I will describe more about this chiral deformation later on. Actually, this is going to be main part of the talk, main motivation. Then this functor, or push forward, in physics, it's called integrating out massive modes on X, or compactify over X to get an effective theory in 2 dimensions. That's a physical notion of this push-forward functor. Now, here's the interpretation for this integrable hierarchy from this story. It's actually universal. It's quite interesting. So first of all, if you try to compute the leading terms of this push-forward, it turns out this leading term is computed exactly by Saito's primitive form and this Barnikov-Kansevi semi-infinite period map. And actually, if the internal geometry is just a point or A1 singularity, this exactly produces this exponential function I explained in the beginning. And then, because it's push forward is in the category of so-called B-way quantization, there's so-called B-way mass equation. And this mass equation exactly produces the equation for integrable hierarchy. So this is something you get for free. But this is the main motivation for this introduction for this talk. Now let me explain. You see, like the important thing here is about the so-called B-way quantization. So I will give a brief account of this method. The B-way formalism arises in physics as a general method to quantize the so-called gauge theory. And there are a bunch of data. For example, this B-way algebra is an algebraic structure. And also, their output of this B-way quantization is a so-called mass equation, I will explain. And then there's a mathematical framework for doing this. It's called a renormalization. So I will briefly explain these 3 points. So let me introduce some notions a differential BV algebra is going to be a triple, AQ delta, where A is a graded commutative algebra, and a Q is a derivation, square 0 is like a differential. A delta is called a BV operator, and again, it's degree 1 operator, square 0, but it's not a derivation. And the failure of this one being a derivation defines so-called BV bracket. And finally, these two operators are compatible. We're going to call this data a differential BV algebra. I'll explain where this one comes from later on. But so here is a toy model for this differential BV algebra. Suppose you have a -1 shifted symplectic DG vector space. So this means the V is a graded vector space, Q is a differential, omega is a symplectic two-form, compatible with Q, but actually has degree -1. And this is the most important shift in contrast to the usual symplectic geometry. So in particular, you identify the dual vector space with the vector space itself, but shift degree by 1. So you change the parity, change boson to fermion, fermion to boson. And suppose then you study, for example, you look at the Poisson kernel of the symplectic form. And under this identification, this Poisson kernel is an element of a symmetric 2 tensor. This is also because of the change of the parity. Then you can construct a differential BV algebra from the data as follows. You look at the polynomial function or formal polynomial functions on this vector space. And then with a differential induced by Q, then you can obtain a BV operator by contracting with the Poisson kernel. So if applied to a polynomial, then you can choose any two of them, pair with K, you get a number, because this is lies in dual, and it's like lies in the vector space itself, the symmetric 2 tensor. And then you get a differential BV algebra. And the slogan here is that if you start with a -1 shifted DG symplectic space, and you get a differential BV. And that's actually a very naive toy model. The toy model, I just mean like this is finite dimensional. Now we're gonna explain a bunch of notions from the data. First one, suppose you have a differential BV algebra. An element here, which is an element of this algebra, valued in the formal power series in H bar, is said to satisfy quantum BV mass equation if such a thing holds. And actually, this equation somehow it somehow says like something is closed, and is equivalent to this kind of equation. And if you go to the classical limit, you're looking at the leading H bar order, A0, then this equation becomes something like that, which is going to be called classical BV mass equation. So the meaning of this equation is the following. This quantum mass equation actually arises in physics as a so-called quantum gauge consistent condition for the measure given by this function I. And also, like the classical mass equation, this one implies that this operator squares 0, which describes the infinitesimal gauge transformations in the so-called BIC formalism. And in mathematical terminology, this data describes a so-called homotopic Lie algebra or L-infinite algebra. And this relation to physics is the following. Like, suppose you start with any kind of classical action with a gauge symmetry, and this data can be completed into a solution of classical mass equation by so-called adding into the Gauss field, anti-fields, and so on. And that's the classical data. And then you can study to quantize the gauge theory by solving the so-called quantum mass equation. And that's the meaning for this equation. Now let's come back to life. We were discussing some toy models, but actually in real life, to apply to geometric situations, in particular some differential geometric models, the quantum field theory actually describes the infinite dimensional geometry. And this toy model, this triple, VQ omega, it's going to be modified to the triple as follows. So this is a real life case. This vector space is going to be replaced by this E, which is given by all possible smooth sections of some graded vector bundles on a manifold. So this is a very big space, infinite dimensional. And this differential structure comes from differential operators on this vector bundle, which make this one as a elliptic complex. For example, this can be like the Ram complex, the Boole complex, and so on. That's fine. We can work with that. And then we need a symplectic two form. And in the real life, if this symbolic two form is given by something local, so it's a local pairing on the bundle, and integrate it. We can do that as well. Then, to perform the construction, we need the functionals on this space. So the linear functional on this vector space. This is a starting point. We're going to be a little bit careful, because the linear dual of this space is given by distributions, because we have a subtle topology on this infinite dimensional space. And by the way, it is also fine. Now we need a tensor product. And there's a well-defined tensor product in the category of distributions. We can take this so-called a completely tensor product, and which give rise to distribution on the product space. That's also fine. So we can take symmetric tensors to get these functionals on this space. There's no problem for this one. Now, the next part is the trouble. To perform the B-way construction, we need to inverse the Poisson kernel of this the symplectic pairing. And because this pairing is given by something like integration, the inverse of the integration is given by a delta function. So we can view this delta function as a distribution supported on the diagonal of the product space. But this is actually the trouble, because then we perform the construction we just described for this toy finite dimensional model. This operator is not defined, because the way we define this operator is by pairing this kernel with functionals from here. But this is given by distribution, and this is also distribution. And you cannot pair distributions. So this is a EO-defined. And this is a famous problem in quantum field theory, which is called the UA divergence. And in particular, this is the place where the so-called renormalization is required. And actually, there are many ways to do renormalization. So I will just explain one possible approach, which is going to be very convenient for our application. So it's Castello's homotopic renormalization. This approach, actually, the idea of this approach is very simple. By elliptic regularity, I mean, this is a cohomology of the distribution, essentially the same as cohomology of smooth functions. So now the idea is that we can replace the original singular stuff by something smooth using this isomorphism, and then try to remember the original way in the homotopic, original theory in a homotopic way. That's the basic idea. So how this works? And roughly speaking, first you try to find a distribution, Q-exact terms to make this one smooth, and that's the previous equation. Then once you get something smooth, you can define this B-way operator by pairing a smooth kernel with a distribution. So now this is very defined, no problem. There's no UA divergence. Then it do the same thing as we did for this toy model, and this triple become a well-defined, mathematically well-defined differential B-way algebra. And then, as the formalism suggests, you have to understand a different choice of this regularization. And if you look at any two possible different regularizations, they're actually related to each other by the so-called, particular, very, very explicit homotopy. I'm going to call this connecting homotopy by this homotopy RG flow. I'm not going to explain the formula for this one. It's going to be something very explicit. And finally, the way you quantize a theory by solving quantum mass equation is also formulated homotopically. So here's the cartoon for the situation. So this is the original point where we want to do the quantization, which is EO-defined because of this UV divergence, a renormalized point. Then you go to a nearby point, choose some kind of regularization, get a well-defined B-way structure, and try to solve quantization there. And they have to study all the possible regularizations, and any two of them are related to each other by some homotopic equation. And this is like we do this kind of residue in algebraic geometry. Like to define residue, one way of doing this is like you deform your function to be a bunch of Morse type functions, and then you can define the residue there and show like it's independent of choice of the perturbation. And this is a very similar idea, although in a homotopy way. And we're going to call this theory UA finite if the original point exists. And this is actually a very lucky situation. But that's the cartoon for doing this quantization process for this particular gauge theory. Now we're going to apply this one to study a so-called Chiral deformation of conformal field theory. And this I mentioned in the beginning that actually this is arise from understanding the integrable hierarchies for any Calabi-Yau geometry. So here are some examples of this two-dimensional theory. Some famous examples of so-called free CFT, like a free boson, a so-called basic system, and beta-gamma system. This is a fermion, this is a boson. We're going to understand the following problem. We're going to understand the B-quantization in 2 dimensions. So this underlying manifold is 2 dimension for a so-called Chiral deformation of free CFT of the following form. So the free part is given by this data. Then I'm going to deform the theory by adding into some interaction terms. And this interaction terms is something local, consistent, given by some kind of Lagrangian density, but it involves only holomorphic derivative. So that's why it's called a Chiral deformation. So basically, we're going to understand this homotopic B-quantization for this particular kind of Chiral deformation to understand what's happening for integrable hierarchies for Calabi-Yau geometry. It turns out that the way you understand this, the homotopic solution is very nicely organized by so-called vertex algebra. So vertex algebra is some kind of algebraic structures in 2 dimensions. So roughly speaking, I'm going to just list a bunch of very key structures. So vertex algebra is a vector space V with structures, for example, the most important one is the so-called state field correspondence. And this element here is mapped to an operator acting on the vector space itself, but with a formal variable, let's call this one Z. And then, by the way, without this parameter Z, this is like the usual algebra structure. And then you have a vacuum vector, which give rise to the identity operator, and translation or locality and so on. I will not list the full axioms. But the most important data from this vertex algebra is the following. You can define a so-called vertex operator expansion for fields using this state field correspondence. And sometimes we're going to just write down the singular part of this data using this notion. And the picture is the following. So suppose you think about this one as limit in 2 dimensions. And the usual algebraic structure is like you look at the fusion rules, combine operators. The 1 dimension, the only one way to combine, you got associative algebra. But in 2 dimensions, like when you combine operators, somehow you have to remember the angle. So that's why you have Fourier modes. So you got an infinite number of this kind of product structure that is collected by this OPE. That's the rough idea of this kind of a vertex algebra. And from any kind of vertex algebra, you can get a Lie algebra. And this Lie algebra is given by all the Fourier modes of these vertex operators. For example, as a vector space, this is spanned by all the possible choice from these vertex operators and look at all the Fourier modes. And there's a very explicit Lie bracket, which is completely determined by the OPE. So this is a very straightforward construction. So this is like give rise to some kind of current Lie algebra. Now, let me give you some examples. Suppose H is a graded vector space with a degree 0 simplicial pairing. Now we can obtain a vertex algebra structure on the free differential ring. So this is like a free polynomial ring on this with a differential operator formally. The AI is the basis of the vector space. And this OPE on this vertex algebra is generated from this basis by the OPEs of any 2 elements of the H. The OPE is computed by this kind of a singular term. So the bracket here is given by the sympathetic bracket. And you have the order 1 pole. And actually, you can see like this example is basically a combination of the so-called BC and beta gamma system we started with. Now, we're going to use this one to understand this 2-dimensional chiral deformation. So we consider quantum field theory in 2 dimensions. I mean, we're going to work with a flat case, but actually this works on higher genus curve as well. So let's, for simplicity, work with this following case, like C or C star elliptic curve. The flat surface. Again, H is a graded symplectic space as before. Then we can get the following triple, the BV triple. First of all, the space of fields is given by the Boole complex on this surface valued in this H. The differential is given by a d-bar operator plus some kind of holomorphic differential operators. And then you have a -1 shifted symplectic pairing. So if you have any two elements from the fields, you take the pairing for this H factor using the symplectic form, and you integrate against the holomorphic form here on the Riemann surface. And you basically get a triple in the same formalism I described in the quantum field theory case. So you get an effective BV formalism. You can basically you can study to perform this quantization in a homotopic way I explained by looking at all the possible regularizations and study the homotopic relationship between any two of them. So now let me describe the chiral deformation. So this actually chiral deformation somehow is described by exactly this Lie algebra from this associated vertex algebra. For example, as I explained, like this element, this vertex algebra as a vector space is a free differential ring. So if you pick any elements here, it's like polynomials, it's differential polynomials. AI is the element of the H2. Then you can construct a local functional on the space of fields by, for example, this element means like you pair AI with phi on this H parameter, you get some differential forms, you take the wedge product and integrate. And this actually gives rise to all the possible local Lagrangian density with holomorphic derivative. So this is how these two data are related. Now, this is the main theorem today. So if you consider the following two-dimensional chiral deformation, so this is an interaction term which corresponds to an element, an arbitrary element from this vertex algebra, the Lie algebra of the vertex algebra, any kind of chiral deformations. Now, the statement is the following. The first one, the theory is UV finite. So, I mean, I drew a picture before. You basically can understand the theory by going back to the original point. So if you do this regularization, go to this point, and you can take the limit back. This is the first statement. I'll explain more about this later by some examples. Secondly, if you try to solve this UV mass equation homotopically, so you have to solve this one at any point and satisfying this kind of compatible conditions, then because the theory is UV finite, you can understand this equation at the original point. It turns out that this homotopic solution of quantum mass equation is the same thing as solving this equation. So this is like a Morikawa equation for the differential gradient Lie algebra for this guy. The delta is the holomorphic differential operator from the Q, and the bracket is the Lie bracket. So this single equation actually describes the whole homotopic solution of the quantum mass equation, and this makes life much easier. And finally, if you put the theory on an elliptic curve, and you try to compute the generating functions, they're going to be some kind of almost holomorphic modular forms. And it's not holomorphic, but it has a modularity property, and but I actually have this following form. Like it has a very mild anti-holomorphic dependence on the imaginary part of tau, polynomial dependence. So fk tau is something holomorphic and of this type. But the whole thing has a modularity property. So I will try to explain the content of the theorem and application in some example. So let me start with the first part. Let me first explain the UV divergence, the UV property and its modularity. Actually, it turns out to be something very interesting. So let's consider the following example. Let's consider chiral deformation of free boson on the elliptic curve. This is a free boson we mentioned, and this is like a cube interaction. And this is an example related to a mirror symmetry on the elliptic curve, also studied by Roper digraph. For example, if you look at this, it turns out like the way you quantize this particular action function amounts to do some kind of Feynman diagram constructions. And this is one example. It's a particular two-loop diagram. And then the way you evaluate something, the quantity like this, is by performing, put so-called a propagator on this edge and integrate it on the manifold. And for this case, it's given by integration on the elliptic curve of the following function. So the propagator here is given by two terms. The first term is given by this Weierstrass P function. The second term, E2 star, is the first term is the second isosceles series. We know this is not a modular, but it can actually correct this one to be modular, but with a mild anti-holomorphic dependence. So this is one example of a so-called holomorphic, almost holomorphic modular form. But that's the propagator that you find from this theory. And you want to basically evaluate this two-loop diagram. And I mentioned in the previous theorem, like the series will be finite, which somehow means that there's no divergence when you try to evaluate this integral. But actually, this doesn't sound correct, I mean, in the first thought, because, for example, this integral, if you try to integrate the cube, like Weierstrass P function to the third order, and this Weierstrass P function has an order 2 pole. And in particular, this one has an order 6 pole. And why it's going to be convergent? Actually, this is a place where this kind of a homotopic renormalization is very smart. Because when you evaluate this term, you first have to go back to the nearby point at some particular regularization and evaluate and then take the limit back. And it turns out that if you do this process, to take the limit back, the limit actually exists. And it turns out that this limit can be geometrically understood in the following way. And this construction, I mean, is a journey in progress with Jiezhou. So let me try to explain. This is a purely algebraic geometric interpretation. So let's consider the following exact sequence on the curve, or actually on any Riemann surface. So the first one is a sheaf of a constant sheaf. The second one is a sheaf of meromorphic functions. The third one is a sheaf of abelian differentials of the second kind. So this is like holomorphic differential. So because this one means like this is a meromorphic one form which has no second order pole. So that's why locally it's exact. So this is actually an exact sequence. And now, then you can somehow view this kind of object, which is the object to be integrated on the elliptic curve, as an element of the following cohomology class. So you pair this data as something which lies in this sheaf, and the d bar thing basically contributes to the H1 of this bundle. And then, because this one is the exact sequence, H1 of this sheaf goes to H2 of this one, which is one-dimensional, that you can integrate to get a number. And this integration map, this connecting map plus this integration, is exactly the renormalized integral for this looking divergent expression. It turns out this algebraic geometric description works for any kind of Feynman diagrams, and actually also works for any Riemann surface. This explains why the series will be finite. And somehow this is related to a physics method, so-called a point splitting method, to understand this UV property. But this is somehow a more intrinsic way of doing this. Now, with this algebraic geometric interpretation, you can do many calculations. For example, you can evaluate this cubic integral. And with this connecting map, you can compute by the following terms. Like this is a Eisenstein series, E6, E4, E2 star, and E2 star cubed. And this is like examples of almost holomorphic modular form. And you can go to the so-called tau bar goes to infinity limit. And then it's funny that this 2D integral under this limit, which in this case amounts to replace E2 star by E2, becomes a acycle integral. It's like a line integral, a loop integral. And this function just become like the quasi-modular forms. E2 star goes to E2 and so on. And this is an example computed by Michael Dokolev, and also used by, for example, digraph in describing the mirror symmetry on the elliptic curve. But this data is mostly computed in physics literature. It's really a tau-bar goes to infinite limit of a particular more intrinsic modular expression. So this is something quite interesting. So this explains the first part of the theorem on this UA property and the last part of the theorem on this modularity. Now I'm going to describe the second property about this homotopic B-way mask equation in terms of this Mori-Cardan element of the Lie algebra. So I'm going to explain this one by an application to this higher genus mirror symmetry and also to this integrable hierarchy. So this is the one I mentioned in the beginning, that on the B side, it can actually find a full generalization of the original Cordova-Spencer theory in our sense. And then the field content of this kind of B-field theory is given by the complex. So this is given by polyvector fields with one formal variable t. So this one is all of these anti-holomorphic forms valued in this holomorphic polyvector. And t is a formal variable represents this gravitational descendant. And this differentials d bar plus t del, and del is a divergence operator with respect to the Calabi-Yau volume form. So it can view this one as a homotopic version of this volume preserving vector field on this Calabi-Yau geometry. And the B model amounts to somehow gauge this symmetry to get something related to the deformation of Calabi-Yau geometry. So as mentioned in the Professor Junli's talk, actually people use this original type of the Cordova-Spencer theory to understand the higher genus invariance in the B model on quintic. For example, this Yamaguchi-Yau, and later on this Huang-Clam, etc. A lot of people's work by solving this holomorphic normal equation. Now we just directly try to understand what's really happening for this quantization. So it turns out that the way it is quantized can be described using this B-way quantization method. So I will just explain by this example. So we specialize to a elliptic curve case. Then this is only one-dimensional, so you have only one vector field. There's no higher polyvectors. There's two components, the book complex and the book complex valued in this holomorphic tangent vector. And this means like shift degree by 1. Then you can collect this data as a Dubois complex valued in some kind of gradient vector space. And from this expression, you see like this gradient vector space is given by this formal power, this ring, like T, the degree 0 elements represent this gravitational descendants. Theta has degree -1, represent this tangent vector. Now we're going to formulate the B-way quantization formalism for this data. So first of all, this is already in the same form as I described in our two-dimensional setup. Now the differential is given by the following. Like this is the first one is the d-bar operator. The second one on this expression is given by delta of this type. This is basically the divergence operator for this Calabi-Yau volume form. Now, the next part about this B-way structure, it turns out this particular example, the Poisson kernel for this shifted symplectic structure is degenerate. You actually got a Poisson structure instead of symplectic. And actually, the way you use the B-way kernel is to write down the so-called OPE for the vertex algebra. So I will just directly give you the answer in terms of this vertex algebra. So we're going to represent an element of this field by the following data. So this can be viewed as coordinate on this space. So in terms of this expansion, Bk is an element here of the double complex. Eta k is also element of the double complex. So this is how we parameterize the space. So we think about this Bk and eta k as something like a field. Then from this parameterization, the OPEs of the field are generated by, first, if you look at the OPEs between the B naught, and this singular term is given by this order 2 pole, which represents the fact that they come from a free boson, and all the other OPEs are 0. And this is this is why the theory actually is Poisson instead of symplectic. The OPEs are quite degenerate. But that's fine. I mean, this is something we can work with the Poisson case and do this quantization. Now, sometimes people say, like, this data has a non-trivial dynamical property which contributes to the propagator. So this is called a dynamical variable. There are other stuff. They don't propagate. So this is called a background field. But that is the data for the big curve. Yes?
So is the Leo rule that corresponds to this the Heisenberg algebra?
It's a Heisenberg algebra plus a bunch of holomorphic vertex algebra given by this background field. So it's a lot of data. Yes?
Sorry.
This one, the B0 leads to Heisenberg vertex algebra.
And the other
This one as well as just some holomorphic data. There's no poles. So like holomorphic vertex operators.
so
Abelian.
it does not correspond to an algebra, the other one.
Let's say this is a background field parameters. So there's no OPEs. Yes. So the essential part is the Heisenberg vertex algebra. And then that's why in solving this quantum B model, I mean, in this example, you will see like this chiral deformation of this free boson arising from this Heisenberg vertex algebra. I explained the solution. So the theorem is that there is a canonical solution of quantum mass equation for the species theory on the big curve. Actually, this theorem is proved by the previous theorem that you can identify the solution of the quantum mass equation in terms of a Morikadan element of a differential graded Lie algebra. Then you can analyze the deformation obstruction complex for this DGLA. And it turns out this DGLA has a simple form if you do a so-called boson-Fermi correspondence. And there it can be computed directly, I mean, to prove this theorem. So this is like a abstract nonsense from deformation theory. But now I'm going to give you some concrete feeling about this data. As you mentioned, like this is like a Heisenberg vertex algebra. So now we can describe the following data. So we just basically work with the B0, which is related to the Heisenberg vertex algebra. And we look at a small sector where we put these parameters to be like this. When k is bigger than 0, we set this one to be 0. And the eta fields, we set this one to be constant. And this property somehow is mirrored to a model data, which is called a stationary Gromitian invariance. So this is the B model version of the stationary sector. And this can be viewed as some kind of initial data on the background fields. So here we basically say like we phrase the background field to be this kind of simple data. So in this so-called stationary sector, I can write down the action functional exactly as follows. So the first part is the free boson. Then this interaction part for solving this BCU theory is given by something rather explicit as follows. So the B0 is the first derivative of the bosonic field. That's why you have the OP as the second order pole. And this WK is called this bosonic realization of the so-called W1 plus infinity algebra. It's this kind of a complicated form, but in terms of Fermi's, it's very simple. So the classical limit of this action functional is given by B0 to the case order, and the other stuff is given by some kind of H-bar quantum corrections. And that is the exact expression for the solution of this quantum B series theory. So let me explain to you what's happening for this what's the meaning for this quantization. So in this small sector, the BV quantum mass equation turns out to be equivalent to the following equation. So the previous operators, this is like some operators in this Heisenberg vertex algebra, and the BV mass equation implies that the whole thing, the operators commutes for any kind of choice of K and F. So basically, you find infinite many commuting vertex operators, and actually, this is a consequence of B-master equation, and this is exactly the way we solved the previous slides. And this expression somehow is uniquely determined by this equation, this integrable hierarchy equation. And if you go to the classical limit, and in this case, as mentioned, like this slides, the classical limit of general cell data is given by this polynomial. Then you discover this kind of Hamiltonian function, and the classical limit from this OPE leads to the Poisson bracket of the field as follows. And this is exactly the one I described in the beginning of the talk, that if you look at the exponential function, and you look at the power series expansion, which you'll find these polynomial functions, and you find the infinite many commuting operators, which leads to the expressionless KdV integrable hierarchy. And that's what's happening here. And the above term is a quantization of the system. So this explains somehow the observation we made in the beginning, but actually there's something more precise I will try to explain. So with this data, you can compute the higher genus invariance from BCOA theory. For example, as I mentioned, like if you compute the generating functions for this quantum BCOA theory, they're all given by these almost holomorphic modular forms. And this top-bar dependence is a famous holomorphic anomaly. And it actually can compute something rather explicit in the stationary sector. And this top-bar goes to infinite limit of the generating function is given by a character on this Heisenberg Vertex algebra of the following form. It is generated by these Hamiltonian functions. And this y exactly coincides with the stationary Gromitian invariance on the mirror elliptic curve, which is computed by Okounkov Pandare Panda. So this mirror theorem in this example basically is a version of Bossa-Fermi correspondence. So their result computes things in terms of Fermionic vertex operators. And here is bosonic, and they are identified. And this leads to a higher genus mirror symmetry. If you look at when the case k equals 1 for the cube interaction, this is the original work by Digraph on this mirror symmetry stuff, and Herzberg covering stuff, versions of this mirror symmetry. So here's the remark. Actually, the way we understand this B model and the integrable hierarchy is the following. The way we understand the theory is like we can understand this theory on the curve as a theory from a product space, a point across an elliptic curve. This is a rather trivial observation, but actually it's exactly this observation that for the point, we see KdV integrable hierarchy. Now you can do something more general once you understand that this is calculation. You can put any Calabi-Yau geometry and look at this trivial fibration, the product space. Then somehow you construct a so-called push-forward functor, which amounts to compactify over this Calabi-Yau geometry. You get an effective two-dimensional chiral deformation of the CFT. Then again, this mass equation implies that you're going to find infinite many commuting Hamiltonians. And this one turns out to be related to Duran-John's principal integrable hierarchy. And this is a joint work with Wei Chang, He, and Phil Sun Yu. And also, in the Landau-Ginzburg case, you can do the same construction. You can put a BCO theory on the Landau-Ginzburg case, do this twisting. And it turns out that the classical BCO theory is equivalent to Saito's theory primitive form. And then the classical Hamiltonians, like I explained in the beginning, somehow the same thing, but by replacing this function by the so-called primitive form. And you also expand the primitive form. And there's a perturbation formula to compute this expansion as developed with Chandon Lee and Kyoji Saito, that I can compute these Hamiltonians like recursively. And this leads to a way to understand these integrable hierarchies universally from this the B model geometry. Yeah, thank you very much for attention.
Can these techniques be used at all for orbital pictures?
This construction Yes. The problem is it depends on whether you want to work on the A side or B side. I don't have a good theory for the orbifold B model since. Actually, we are somehow working on this, formulating this orbifold B model in terms of this Hochschild data. They can do something similar in the Hochschild homology since. Then you can understand what's happening in the orbifold B model. But this is something still not done yet. Yes.
Okay, so let's thank the speaker again.